Welcome to the fourth and final episode in our 2022 webinar series. I'm Julia Speaker, Project Manager and Cast It Team Lead in the American Metal Casting Consortium's Innovative Castings Technology Program. Cast It is an acronym for what we do, Castings Advanced Systems Technology Integration Team. Our webinars are funded by the Defense Logistics Agency. The theme of this 2022 webinar series is the project management by a new awardee that should precede the manufacturing engineering of the casting processes in a legacy casting launch. This project management ahead of time manufacturing thinking and planning is especially important in the context of a cold start new awardee who is a machine shop. In the 2021 webinar series, we focused on preparation for successful first article approval of a DLA legacy casting, and we coined the term cold start. For those of you joining our series for the first time, I will briefly review what a cold start means. Attempting a successful DLA legacy casting launch, a cold start is especially difficult because all of the prior successful manufacturing engineering of the tooling and processes has been lost. A cold start is difficult enough for a metal caster who's familiar with the nuances of casting tooling construction and casting manufacturing processes. It's even more difficult for a machine shop whose core business is much different. This difficulty is relevant because machine shops are now 70% of DLA's new legacy casting awardees. The essence of project management is to clearly identify all that is required in the finished machine casting, understand it, and put all the major steps in a timeline. The idea is to think of everything that matters in advance and not forget anything. The objective is to not back up to fix mistakes or redo steps. For complex, high-specification DLA legacy castings, not fixing mistakes and not backing up to redo steps is a tough challenge. Now, in this part 4, we will address the project management forethought required to finish the as-cast surfaces of a DLA legacy casting made in either the air-set sand or investment casting processes. Finish those as-cast surfaces so that the dimensional capability is protected, surface finish is protected, and solidification integrity is assured. Now, notice that I emphasized the finishing of as-cast surfaces. It is one thing to form functionally, structurally, and dimensionally capable as-cast surfaces in the molding and pouring shop, but it is another to protect and sustain those as-cast surfaces in the finishing department. It is from those as-cast surfaces that the finished machine surfaces are formed in the correct positions and planes to meet the machined tolerance requirements. The significance of as-cast surfaces can be put in perspective with these underappreciated insights about finished machined castings. Castings with very simple as-cast geometry machined to more complex net shape are still 80% or more as-cast in their final net shape. Castings with more complex as-cast geometry, as are typical DLA legacy castings, are 90%, 95%, and sometimes even more as-cast in their final net shape. Those high percentages of as-cast geometry means that the as-cast features are important in the casting designs functionally, structurally, for stress control and component durability, and sometimes assembly with other components, using just the as-cast surface or surfaces. A common example of the latter is as-cast fastener holes and smooth, acceptably flat as-cast bolt-up surfaces. Especially important to machine shops are the as-cast surfaces that are used for setup in the first machining fixture, and sometimes part of the setup targets for a second machining fixture. Those as-cast setup features should be datums in the design of the casting, and those features should have datum targets defined on them. For legacy casting 2D drawings, those datum targets are probably not defined, and the metal caster and machine shop must define those targets in advance before anything starts. Foremost, this part 4 summarizes why, how, and when as-cast surfaces should be protected in their original dimensional capability from the design of the mold cavity and its processes, and their conformance to the drawing's dimensional specifications. While protection of as-cast dimensional capability and conformance with tolerances is paramount, the next most important function of casting finishing is verifying, and sometimes upgrading by in-process weld rework, solidification integrity. Solidification integrity in castings is the basis of mechanical properties and casting durability in cyclic life. Fundamental to achieving mechanical properties in heat-treatable alloys is the equipment and process controls for controlled heating, controlled time at temperature, and controlled cooling of the casting to accomplish the specified mechanical properties. Whether heat-treated in-house or by an outside heat-treating partner, it is a process that is well understood and robust. Since verification of heat-treated properties is usually accomplished with test coupons that are as cast separately by one method or another, the properties from tensile tests, impact tests, and bend tests, for example, are representative of the alloy's capability, not necessarily a local high-stress region in the actual castings. So, in this Part 4 overview of project management of casting finishing processes, we address testing for solidification integrity of high specification castings, both on their surface as well as in their interior. If a local region of a casting is critical structurally, the design will include specifications for non-destructive testing of the casting by surface methods and/or by radiography. If the solidification integrity meets those NDT specifications, then the results of heat treatment and mechanical testing of coupons will assure that the casting has the strength and durability intended in its design. Today's concluding episode explains all this thoughtful project management thinking at the outset, before any finishing processes just start. To characterize the finishing of as-cast surfaces in either the air-set sand or investment casting processes will be our Cast It teammate Mike Gwynn. Mike is our expert on casting design and manufacturing engineering, and Mike has a background in manufacturing operations management, which includes project management. We suspect that project management forethought of the finishing of as-cast surfaces, even before mold cavity tooling is designed and built, even before manufacturing engineering of the mold making process, is a fresh idea. After Mike's focus on the forethought required to assure the finishing processes protect the casting's as-cast dimensional capability, I'll return to address the roles that finishing plays in assuring that the casting meets its solidification integrity requirements. Now, here's Mike to characterize the effect of finishing processes on dimensional capability and cosmetic appearance of as-cast surfaces and how to use care in those processes to protect them.
Thanks, Julia, for that insightful first segment in the finishing of castings in general, and specifically the finishing of castings made in the air-set sand and investment casting processes. Building on the whys of casting finishing that Julia introduced, let's now address the when the protection of as-cast surfaces begins and then how to do so. Perhaps surprisingly, finishing begins when the casting is still in the mold cooling. At this point, the foundry and pouring teams are less interested in the casting and more interested in moving the molds to shakeout in the case of air-set sand castings or to ceramic shell removal in the case of investment castings. However, removing the casting from its mold too quickly risks distortion of the thin walls and delicate projected casting features. Such distortion will immediately violate as-cast dimensional tolerances, and the idea of protecting the as-cast surfaces has already been compromised. The consequence of accidental casting distortion from removing the casting from the mold too soon while the casting is too hot and too soft depends on the alloy. Most casting alloys can be straightened, although brittle cast irons cannot, even if heated to high temperature. Ductile irons can be straightened in varying degrees depending on the strength grade. Softer grades can be straightened more than the harder ones. Some alloys, especially the steels, can be straightened at room temperature without causing a crack. However, doing so means that the metal is being plastically deformed in local spots to enable movement of an entire bent or twisted feature. Plastic deformation shortens the cyclic life of a metal component. Perhaps the casting only has a static structural purpose or no structural purpose at all, but the finishing folks probably have no idea about any of that. It's proper practice to heat the casting to an appropriate temperature depending on the alloy to prevent plastic deformation while straightening. That way the casting's structural life, if that's important, won't be compromised. Here we see a high specification, very complex, high alloy steel casting being checked for straightness in a quick 3D printed, durable nylon dimensional checking fixture. Usually castings are straightened by a skilled operator with a press, a torch, and manual straightening blocks of various shapes. The checking fixture is used over and over to verify the progress of the straightening increments. A very effective tool for protecting the as-cast features that are most important for casting machining setup and as-cast features used in final assembly is a functional gauge. A functional gauge is a finishing process holding device that targets a casting on its primary datums and clamps or touches it on other surfaces important to the first machining fixture and or as-cast final assembly features. Every casting passes through the functional gauge in its finishing process step. Therefore, it's 100% dimensionally effective. Here's an example of 3 functional gauges used in assuring dimensional compliance of a steel casting used in the rear suspension of an 18-wheeler tractor. The casting is used as cast with no machined surfaces in its final assembled net shape. Shown are 2 views of the green sand casting, 4 of which are used in the suspension supporting airbags. Accurately placed and accurate cores form the assembly surfaces in the suspension. This is the first of 3 functional gauges. This one sets up the casting on the primary datum A, which is the axle seat. The casting is clamped against the tertiary datum C, which is the circular profile of the airbag seat. The functional purpose of the fixture is to assure that a twist drill passing through the cord as cast bolt hole is centered, only assuring that there is no plus metal on the inside of the cord hole, but actually not drilling an elongated shape in the hole. The casting rests upside down on the second functional gauge set up on the secondary datum B, the face of the airbag seat on each end of the casting. A simple piloted end mill kisses the face of the surface on which the airbag's bolt washer sits. Not machined, just kissed to assure that the tolerance of flatness is maintained. 5 castings fit up on a simulated datum A axle housing. The beam's arm fit between rectangular tabs. The function is to hold the beams for final cosmetic grinding of the mold parting line and core match lines. Design and construction of the functional gauge are 2 homemade steel castings, enabling the castings to be spun around on a Lazy Susan. The rectangular tabs assure that each casting is not bent or twisted. A steel stripped wooden change piece simulates the axle housing. 60,000 castings in the 2 axle angle versions were shipped each year, assembled on trucks completely as cast, no machining, and virtually 0 casting complaints or returns. Now let's address the how finishing is done for complex high specification castings to protect their as-cast surfaces. The first finishing process in how is to remove the gating system, the risers, and the vents, which are the additions to the casting's design geometry to fill the mold, feed solidification shrinkage, and remove gases in front of the liquid metal as it flows into the mold. For short, we call those geometries plus metal chills in the mold walls of sand castings process interface geometry. The first realization about process interface geometry is that its connections are not as cast. The markers from those connections are manufactured by finishing operators using various means of cutoff and blending. The intent of blending is to make the markers look as much like the surrounding as-cast mold surfaces as required by the casting's dimensional and surface finish specifications. But the marker surfaces don't have the dimensional tolerance capability of the surrounding as-cast mold surfaces. And why is that? Well, because a person formed them with a blending tool by hand and by visual appearance as the blending progresses. It doesn't make a difference whether the casting was made in air-set sand or in the investment casting process. The marker is always formed by a person using hand tools and eye-hand coordination. Amazingly, most first article inspectors have no idea of the extent or history of these markers on some surfaces of every casting they inspect. I know I'm exaggerating, being cynical and sarcastic, but metal casters, like I have been, who suffer through first article inspections and meaningless nonconformances, will smile as I say this. First article inspectors encountering a casting are amazed again and again by the presence of draft, let alone the presence of process interface geometry markers. It's like each casting is a fresh encounter. And while I'm insulting people, let me also say with tongue in cheek that machine shops who don't regularly machine castings unknowingly build machining fixtures that target drafted surfaces at different draft offset elevations and then target process interface geometry markers. Then they complain that the castings are defective and won't machine consistently into dimensionally acceptable parts. Well, what to do about this disconnect is a subject that I address in my work with casting design engineers, but it's beyond our purpose in this webinar. What is our purpose is to address reality for high specification, complex geometry castings, specifically DLA legacy castings. That reality that finishing of these process interface geometry markers has to be essentially perfect within the specified as-cast dimensional tolerance profiles and surface finish. It's a lot of work and tender loving care to make these markers essentially perfect within specification, but first article inspectors will not realize the reason for their presence and will not have the original engineering authority available to say, oh yes, those markers need to be there, those are okay in those positions. Well, back in the day, the original design authority and the original supply chain, those informal deviations actually happened. Now, in a cold start, it won't happen. Before moving on to the finishing processes that assure specified solidification integrity, let's define the difference between the fourth kind of process interface geometry and the other three. That fourth kind is markers from the placement of metal chills in the mold walls of sand castings. High specification air-set sand castings in aluminum, magnesium, and lightweight steel castings especially use chills to accomplish the specified solidification integrity and the resulting mechanical properties. Because investment castings are poured in a preheated, very hot ceramic shell mold, chills are not involved in setting up solidification integrity. But chills are very common in high specification air-set sand molds. The blending of chill marks is different than the blending of other process interface geometry markers. First, there's no cutting off of attached geometry. Depending on the fluid life of the alloy, the chill mark may have a thin raised fin of metal defining the edges of the chill as it was set in the sand mold wall. That thin fin needs to be ground flush with the surrounding as-cast sand mold profile. The chill face itself, being metal, will have a different texture than the surrounding as-cast sand mold texture. Some of that difference can be minimized by media blasting the chill face to make it appear rougher. So, what is the thoughtful, advanced project management planning that can address all of these process interface geometry marker appearance and dimensional problems? Well, first, assuring that the upgrading of some as-cast surfaces to finished machine surfaces will be dimensionally conforming and consistent from casting to casting based on machining fixture design that avoids the markers. And second, assuring that the first article inspector, who is probably completely or mostly unaware of the presence and reasons for these markers, will not reject the casting for dimensional or appearance nonconformances. That means doing so essentially perfectly within the dimensional tolerance and surface finish specifications of the surrounding as-cast surfaces. Well, let's now return to Julia, who will put a cap on the project management finishing principles for protecting the dimensional capability of as-cast surfaces. And then Julia will address the roles that finishing plays in assuring that a high specification casting conforms to its solidification integrity requirements.
To finish Mike's segment on protecting as-cast surfaces in finishing processes, let's look at simpler but still threatening finishing practices to as-cast dimensions and surfaces. First, handling among smaller, lighter castings of all kinds. Finishing operators have scores, even hundreds of small castings to move during the course of a single day. The castings have to move from one finishing processing step to another. For the sake of production efficiency, operators have to move the small castings from their workstation to a nearby box for a fork truck to move to the next finishing operation. In the case of light alloy castings, it is typical to toss a process casting into a nearby box. Likewise, brittle cast iron castings are typically tossed only a short distance to prevent fracture. Copper-based castings are typically softer than cast iron, but heavy, so a short toss can result in a dent. Ductile iron and steel castings are both heavy and dent resistant, and they are not only tossed, but thrown longer distances. If features are thin and projected, the long throw and abrupt stop can dent a ductile iron casting and dent or bend a steel casting. The typical DLA legacy casting, especially airframe castings in aluminum, magnesium, and thin wall steels, need to be set up in the finishing process plans for placing, not tossing, as finishing processes are completed. It is also common to move high specification castings from one business partner location to another by truck. For example, from intermediate as-cast finishing steps at the casting facility to a local heat treat shop, or from the final as-cast finishing processes to a local coater or plater. For castings with thin wall projected features, it is important to package them with separators for the transit back and forth to avoid dings and distortion. Non-destructive testing is used to assure solidification integrity on casting surfaces. Freedom from cracks or hot tears tested by magnetic particle or dye penetrant inspection, or casting internal integrity, which is specified levels of acceptable internal porosity tested by radiography. In-process weld rework is used to repair surface or internal integrity anomalies. As always, a repaired surface must include blending of the repair to assure compliance with dimensional tolerances and surface finish in that region of the casting. For castings requiring specialized coatings, when high specification coatings, anodizing, or plating have been completed, there is no backing up to repair a visual surface defect. So be sure to have completed all heat treating, non-destructive testing, and made any necessary surface repairs before sending the castings for coating and plating. Not thinking through and making a project management plan for these handling, packaging, and coating processes is a common reason for backing up, remaking castings, and suffering big delays and big cost overruns. Because of the cold start problem, DLA legacy castings have to be essentially perfect within specifications dimensionally and cosmetically. The risk and cost of first article rejection is just too great. Just starting as usual will result in finishing operators doing what they regularly do, and as usual is normally okay, but in these high specification situations, doing the usual leads to mistakes. These simpler finishing concerns and the more complex ones that Mike defined for us are the kinds of mistakes that our case study in Part 3 detailed. 10 commercial legacy and safety critical replacement part castings for a roller coaster ride took 4 years and 10 months to complete. At worst, even as difficult as the castings are to produce, finish, and machine, a few months should have been plenty of time. Moving on now from protecting as-cast surfaces, let's look at how finishing processes affect solidification integrity. There are 3 finishing scenarios for a high specification casting, requiring verification of specified surface and/or internal integrity. So first, no finishing processes are required. Only non-destructive testing verification that the casting's design geometry and the metal caster's process interface geometry, that is the gating, risering, venting, and chilling, accomplished the required solidification integrity as the liquid alloy cooled in the mold. This is the best and technically achievable result of careful manufacturing engineering of the tooling design, the mold cavity making process design, and the setup of favorable temperature and mass gradients from the process interface geometry system. Second, finishing processes are required to repair cracks in stress concentration regions in the casting geometry from improper straightening or from a rapid cooling quench after a high temperature heat treatment. The in-process weld rework process that Mike described in his segment is readily capable of restoring the casting to its specified surface integrity. To do so with certainty requires a preliminary stress relieving heat treatment to remove any remaining stress concentration that could hinder the weldability of the crack region. Being structural, the weld must be made according to approved weld procedures and performed by a welder who has been qualified to perform this type of weld in the particular alloy involved. The weld is followed by another stress relief heat treatment and dye penetrant or magnetic particle inspection, depending on the metal casting alloy, to assure that surface integrity has been restored. That approval by a qualified inspector is followed by careful surface blending processes Mike described to restore the dimensional tolerance and surface finish conformance. Third, internal porosity beyond the specified integrity class limits is found by radiographic testing. Typically, such porosity is solidification shrinkage, gas macroporosity, or gas microporosity. Radiographic standards for the various casting alloy types are established for these types of porosity and the standard grade levels of severity for each type. Part of a critical service casting's design is to establish the class of acceptable internal porosity. The acceptable level is correlated to the level of transform stress in the region of the casting and the cyclic life intended for that casting. Upon discovery of a non-conforming internal porosity level, the metal caster has two choices: salvage that and all castings by in-process weld rework after excavating the casting to remove the porosity, or two, remake all of the castings. That choice is typically made on the basis of cost and lead time. Since in-process weld rework has been established as capable and robust in restoring casting structural integrity, the choice revolves around the number of castings involved and the cost and lead time to remake them. Internal porosity problems are almost always the result of casting design geometry and the manufacturing engineering techniques deployed in process interface geometry to assure that design solidification problems are overcome by gating, risering, and chilling strategies. That means that if one casting has the solidification integrity problem, then the others also have the problem or on the cusp of having the problem, based on temperature gradient differences from one casting to another. If 5 castings are involved, salvage by in-process rework is the logical choice. If 50 castings are involved, then remaking all 50 may be the least costly and quickest solution. Right here is the reason that in both the 2021 and 2022 webinar series focused on successful launches of DLA legacy castings, we implored the making quick prototypes at the very outset. Those prototypes, quickly evaluated without much finishing, is so powerful in avoiding downstream, weeks later problems with dimensions and solidification integrity. If salvage by in-process rework is the choice, then a complete reheat treatment of the casting is required to assure uniformity of mechanical properties in the weld and in the heat effective zone around the weld, and the careful blending of all weld areas to assure compliance with casting tolerance and surface finish specifications in that region of the casting. To wrap up, since the two 2021 webinars and this 2022 webinar series are a continuum of how a cold start DLA legacy casting awardee can be successful in a very difficult casting launch. I will post in the chat box and in an email to each of you the links for each of the webinar episodes, including this one. And now, let's take a look at the Q&A box for your questions and a couple of discussion topics.
All right. So thank you guys for joining us for the webinar today. I'm going to go ahead and ask the Castit team to unmute themselves and also share their videos if they would like. And Before we jump into the Q&A, I'm just going to take a minute to introduce everyone. So you guys already met Mike Gwynn. He is our manufacturing and engineering expert, as well as casting design expert. We have Keith Sturgill, who's been in a couple of the webinars. He is our expert in all things DLA, as well as has a lot of experience as a metallurgical engineer. And then we have Gary Burrow, who is a 5th generation pattern maker and really all around knowledgeable in all things castings. So I think to start off, we do have a poll question for you guys. So I'm going to pop that up while I continue to just say a couple of things so you guys can read through it and answer, and then we'll go over it and get into the actual Q&A. All right, so you guys should be able to see that now. So while you're taking a look at that, I'm going to go ahead and pop a couple of links in the chat. The first thing being my email. If you are watching this for continuing education credit and you need an attendee certificate, please send me an email and I will get you one. And then the other thing, as I mentioned in the video portion, we do have all of our webinars, so not only this series, but the previous series available on our YouTube page. And those are great resources. Feel free to watch them. If you have any questions, reach out. We'll be happy to touch base with you. So I'm putting the link to our full YouTube page. So we'll give everyone another minute or so just to answer the poll question. All right. So it looks like we're getting a couple of answers. So I'm going to go ahead and end the poll. And then let me share the results. All right. So Mike, I think, do you want to go over the answers to this one?
Yeah. The elements that are important in finishing and protecting the S-cast surfaces on high specifications, especially specification castings, well, removal of the gate, riser, and vent contacts, cut off of the tensile test coupons from a heat-treated keel block is irrelevant to the casting itself, so that one would be false. Grinding of the mold parting lines would be important. Cutoff of chills embedded in the casting surface as well. Chills generally are not embedded in the casting surface. They're not like the gating contacts and the riser contacts. So cutoff is not involved in the chills. You just blend the edges of the chill interface between the chill itself and the mold wall. Grinding of mold core match lines. Those are like the mold parting lines, and those do have to be ground flush carefully. Tossing rather than throwing castings into nearby boxes when a grinding operation is finished. Well, that, either tossing or throwing is, especially on projected thin surfaces, is usually a reason for dents and bent features. And then allowing castings to cool sufficiently in the mold before shakeout or shell mold break off. Yes, that is another process element that is important to protecting S-cast surfaces.
All right. Thanks for going through that, Mike. So it does look like while we were doing our true and false poll quiz, we did get a couple Q&A questions. So just going through those, I think the first one is probably for Mike and maybe Keith. Gary, feel free to chime in, of course. But they said that you didn't mention softening of solution heat treated alloys for straightening. Could you go through that process and then some of the maybe project management considerations for it?
Yeah, that's an excellent observation that we didn't address that specifically, and a great question. The most important solution heat treated alloys are the aluminums, magnesiums, and some of the high alloy steels. And the heat treatment of these alloys involves heating the casting to a critical temperature, depending on the alloy, and then quenching it quickly in a liquid. And that rapid quench puts the precipitates in those alloys, which precipitate and strengthen the alloy's microstructure. It captures those precipitates in solution. And for a short period of time, the casting all over is very soft. So even though it's a complicated heat treating process, it has a great benefit compared to straightening in other alloys because the whole casting is soft for a period of time. And you can straighten all features that have nonconformances in twisting or bending without damaging the casting structurally by causing it to plastically deform. So it's a complicated process, time-limited process, because hardening and aging begins at room temperature. So you got to be quick about it, but it has the benefit of being able to straighten all over all at once. And many of these castings of this type are structural castings in military and aerospace applications where being careful not to damage them is really important. So great question.
All right, thanks, Mike. Keith, did you have anything to add?
Yeah, I had just a little bit. Years ago, when I worked for the Navy, and we did a lot of manufacturing at the Navy depot, so I had some experience with the heat treat shop and machine shop, and so more so with parts machined, aircraft parts machined from stock rather than castings, but same thing sort of applies in both. And so when you quench, I'll just talk about aluminum right now. When you quench aluminum, as Mike said, the metallurgy there is that the precipitates are, when they're heated up to, say, around, for aluminum, around 960 Fahrenheit, quenched in water, precipitates are held in a solid solution there, so the part's soft. And but if you're if you're dealing with an age hardening or a part that hardens with time, you want to make sure you do your straightening right away, because those parts, even though they're dead soft, as soon as they come out of the quench, within hours they start to harden up. So for the aluminum parts, especially these thin aircraft parts, they're very soft and very pliable and easy to straighten. So a good artisan with a rubber mallet or some presses and some go, no-go type templates and a bench to work on can straighten these parts in the soft condition, soft as cast condition, very easily. And it's very important to do it then. Now, if you also, if you can't do it immediately, what some heat treat shops do is they put these parts in freezers or dry freezers and keep them cold until they can do the straightening. But if you leave them on the bench, within a day or so, they're going to start to harden up and they're going to get springy, and you can't really straighten them effectively. So you want to do it as soon as possible, or keep those age hardening alloys very cold.
All right. Great background on some of the logistical issues that you can see pop up with that process. All right. So it looks like the next question is, how long would you recommend for this kind of project management beforehand to take place? And does that cause any more lead time than initially? So I'll take a stab at that first. And then Gary, I know you have probably a fair amount of personal experience with this, so maybe if you want to chime in. So I'd say for a machine shop, maybe 2 weeks once you have a metal caster and a mold cavity tooling builder. It really takes a solid couple of weeks to get that analysis and collaboration among the three businesses. But some of that project management thinking can be done just by the machine shop while you're still making those business decisions on who to choose as partners. And I would say that additional 2 weeks is well worth it, so you don't end up in a situation similar to that roller coaster case study we went through, where it took about 4 years or so to get those 10 parts delivered. So Gary, do you want to chime in with your experience?
Well, typically when you get a RFQ in, you'll collaborate with your potential suppliers right up front, kind of come up with a decision, and each one takes it and works on their quotes for their portion of it. And then whoever the ultimate awardee or quoting back to the government or whoever, then they bring all the pricing together and do their magic on it, and then turn it in as a finished line item. And then each one, of course, has their own lead times and everything involved in that. Cases of, if you're the foundry, then you're going to have your tooling costs on there. Machine shop is going to have their fixturing costs. Some cases when you go out even to paint and that, you may have some masking fixtures or something. So there's a lot of different things to put together in putting a price together. And then a lot of the issue with the government is they don't give you a lot of time. So trying to bring that together in a manner that's within the requirements sometimes creates some of these issues where you're throwing a number at it, you're guessing or whatever, just because you don't have the time. So that can get you in trouble sometimes. So, overall, it is a process, and it may be a little scary if you're not doing it, working with the foundry and all those manners up front. But once you get a team that you're used to working with, then it can move pretty smoothly. But things like that part, which was one of mine that took so long, was we thought we were doing everything right up front, but then we had foundry failures, and they actually took a part on that they weren't really capable, shouldn't have been doing in the first place, and just gave up, handed it back, and then starting our process over again to get another foundry online. And that was a difficult part. Not a people were interested in taking it. So finally started calling in some of your friendship notes and get somebody to take it and run it. And then they ran into more issues than they thought they were going to have. So once we got the castings in, we could move it pretty fast. But and then we ran into some of the issues on the straightening and tolerancing and things like that when we were in final inspection. And then the customer was able to live with all of them, bottom off in first article approval, and was good to go. That's about all I got on that.
All right, great to have some insight from someone with that personal experience. There's definitely a lot of pieces to consider at the very beginning in that short amount of time. One thing I will say is, I know Gary, you spoke about it a bit, and Mike, I believe, also spoke about it in his portion of the video, is choosing those partners. We didn't go into detail, but we do have another previous webinar series. I believe it's First Steps, Mike, if you recall the name, First Steps to Supplying Legacy Castings, that kind of delves more into what you might want to look for in a partner if you are a machine shop. So just a shameless plug for that. You can find it at the link that I put in the chat.
Well, I'm glad you brought that up, because Gary's right here. And what you need to do, because this is, how should I say, one partner removed usually from the relationship that you choose with the metal caster. The metal casters have the relationship typically with the mold cavity tooling builder, which is Gary. And that person is so critical, because all of the solid models, for example, in all their various versions for replicating the 2D drawing, as well as putting the shrink rule, as it used to be called, or the pattern maker's contraction to make the part bigger because it gets smaller after it's cast, and all the things that have to do with designing the fixtures and that all that stuff. There's 3 levels of solid models that have to be built. Well, guess who builds those? It's the mold cavity tooling builder. So you really need to investigate, when you're choosing a metal casting partner, what kind of capability does that Gary type person have? Gary's got those skills at the highest level I've ever met, and finding somebody that approaches Gary really, really helps.
All right, thanks, Mike. So it looks like we have one last question, and that is probably for Mike. I'll keep you talking. And so when you say qualifying a casting, what does that actually mean in context of that first machining setup?
Well, Gary's a real expert on this too, so he can probably chime in and tell me where I've been wrong on this one. But here's the idea of a qualifying fixture, and you're qualifying as cast surfaces in order to set them up more reliably for machining. And the idea of a qualifying fixture is essentially like a box, and you put the casting inside this box that has adjusting screws in 3 planes. And the reason you do that is because the castings haven't been controlled as much as they should have been with regard to bending, twisting, and things like that. So what you do is you take every casting and you set it up on as cast surfaces. And then you basically look at those as cast surfaces that you're going to machine and play with those adjusting screws until you're happy with the amount of machine stock on all planes. Then you basically tighten everything down, and you use spot face drills that are fixtured in certain places on the qualifying fixture that will put little spots on the castings that then are defined where the machining fixture will touch. Well, my point is, hey, you're still touching as cast surfaces, and you're having to do this on every casting, and you're having to play with every casting to equalize, essentially the errors in the as cast surfaces. So my point is, and I don't have a lot of advocates that believe me on this, but I feel strongly is, well, hey, then why not just control the as cast surfaces in the first place, like we're presenting in this webinar, and then just basically use the machining fixture as the last check, that last functional gauge. If your machine shop then, and I did this with my machine shops who were good at machining castings, otherwise I wouldn't do business with them. They would just take my castings and stick them in that machining fixture. And when they clamped my casting, if it wiggled at all, if it didn't just sit flat and clamp down nice, squarely and stably, they would take it back out of the fixture, send it back to me and say, hey, Mike, there's something wrong with this one. And they wouldn't machine it. If it sat down in that machining fixture after we worked so hard to keep those surfaces consistent, and it clamped down snugly and didn't cock or twist, boom, machine it just one after another after another. It's way quicker and a whole lot more cost effective. And I just really believe that is the way to go, as opposed to qualifying, which is slow and expensive. And I don't know, Gary, you probably fight back on that, but that's my 2 cents.
Well, everything you said was correct, except you mixed and matched a little bit.
Go ahead.
So let's start with the targeting, you would call, of those castings in a fixture, which is typically done on some of your more rangy aluminum parts for aerospace, but I've seen it been done on larger parts also. So you balance that part in the fixture. So you're really kind of moving the part around to like a profile tolerance and balancing to get the best you can, which is what Mike said. And then you use that drill spot face tool and target that part. And then the machining fixture picks up directly on those targets for setup. And that basically takes all the potential error out of it. Well, before the days of touch probe, you had to do that. With now the touch probe is involved in machining processes. You can use a touch probe to offset a lot of that. And the parts that you may not be that quite as critical for that, you would have your machine fixture would typically have just hard tooling points. So there'd be certain tool points designated on the drawing that basically you don't grind on those, and then you put them on a surface intentionally that is not a parting line, something that's going to stay very clean all the time. And then that's the tooling point that a machine shop would bump against and set up on. But you can still have some distortion, non-consistency. So there's where your touch probe really comes in. You go in that fixture, you know where the part is, you touch probe off on some few major features, and it says, okay, I'm out of position by 10 thousandths. You just punch that in there for your start point, offset 10 thousandths, hit the button and go. So that really helps speed up the process on what used to take a long time, or potential scrapping on large, like engine bases and stuff. I've seen them have a big template that they throw up there that's got the machine areas. They balance the template out on there till it's good to go, zero their tooling, their machine out to the template, and then hit go and start machining from there. So there's a number of different ways you can do it that are all really doing the same thing. But it's good to know you can get in trouble real quick if you're not doing that.
Right, because mismachining castings is expensive for everybody.
But in the machine shop's mind, it's never their fault. It's always a casting problem.
Yeah, and that's the reason for my smart aleck comments in the middle of my segment.
All right. Well, on that note, I want to thank everyone for participating in today's webinar. This does conclude the webinar as well as the project management approach series, which, as I mentioned before, all the previous episodes as well as this one will be available at that YouTube page. It'll probably take me a day or two to get this one posted, but they will be there for your reference in the future. I am going to post a survey link in the chat. I would really appreciate if you guys take a minute to fill it out. I think it's only 2 questions, mostly multiple choice. You guys can provide your comments if you choose, which we would love to hear. But we really do take your feedback and apply it to our future webinar series. So with that, feel free to reach out to me if you have any questions that are casting related, even if we didn't cover it specifically in today's webinar, and I'll be happy to get you an answer. But thanks, everyone. Hope you guys have a great day and a great holiday season coming up.
Bye, everybody.
Bye-bye.
Bye, everyone.